Hello, Polly and me. We are just here. We wanted to tell you a little bit about what's going to be on the next test. All right, Polly, can you tell them? Polly, they wanted to. Yeah. All right. Anyways, well, I guess Polly wants me to tell you. All right. The test that will be uploaded, and you should have access to it. I'll probably open it up on Wednesday, and then you will have, uh, probably till Sunday to take it. So it'll be in lieu of Friday's class, but you can take it a little earlier if you'd like. Okay? All right. This test is going to be on everything probability, right? So, what did we cover when we covered probability? Well, we started out with the Venn diagrams, right? There were three different Venn diagrams. Okay. Yeah. Okay, Polly. Okay. All right. The three Venn diagrams were, okay, um, the standard one, which has an overlap in it, one where one circle was completely separated from the other one, and the third one was when one circle was entirely inside of the first one, right? So one of the things you need to know is, you know, which of those Venn diagrams do you use to illustrate uh, any specific set of two activities, right? Event A and event B is happening, right? And so you got to interpret that a little bit. You know, are they mutually exclusive? Is one always true when the other one is true? And stuff like that. All right. Okay. Next thing that we covered then were the probability trees. So we need to have you walk through how to build the probability trees. One branch, branching out into multiple branches, multiple going out beyond that. So one of the things that you need to do is understand on each node in that tree, okay, what's the probability of going on one branch versus the other, so on and so forth, right? So almost every activity that has multiple steps to it can be written in this manner, okay? And so we worked through that. A couple of concepts that we came up with there is a concept of independence. Is what happened in the previous branch. So does it matter where on the tree you are in terms of the odds of the next steps happening? Okay. And if things don't matter one bit, for instance, Polly throwing coins off of our tabletop, okay, what she got in the first throw doesn't influence the odds of the second flow. All right. You know, what she got in the first throw and the second throw are independent of each other. So if you are on the part of the tree that had a head the first time, the probability of it getting a head the next time is exactly the same as had we been down on the lower part of the tree where we had a tail the last time, right? If that's the case and those odds never change depending on where you are in the tree, then we say those events are independent of each other. If the odds actually do change depending on where you are, okay, we will say that the events are not independent of each other. I don't like using the word saying they are dependent upon each other. I prefer the not independent of each other. Okay? And the example that we used there was when we had a deck of cards. And in the deck of cards, okay, if someone picked out a heart the first time, The second time, if they did not put that heart back into the deck, okay, if they did not put that heart back in the deck, the odds are going to be different for getting a heart the next time around. If they got a heart the first time, the second time, there are only 12 instead of 13 hearts left in the deck, and there are 51 cards left. So the probability of getting a heart, a second heart, given that you got the first one, would be 12 51sts. On the other hand, if you got something other than a heart, so you were down on the bottom, you didn't get a heart, the odds of getting a heart on the second draw is 13 out of the 51 remaining cards. It's different. Okay? So the odds change depending on where you are on that tree. Right? Okay. So those were probability trees, and we can kind of work those things out. And the probability trees, when we had events that were constantly 2 branches instead of multiple ones, and each event, each branch, okay, would each node would have been independent of each other. We can use that to create what was called the binomial distribution. We gave you the binomial table, which you will be allowed to use on the tests. Okay. And we taught you how to use those binomial tables. Okay. Then we shifted to continuous distributions. We first, before we went to continuous distributions, we talked about the official rules of a probability function. Okay, the official rules of a probability function in the discrete world is that you can make a series of histograms. You can make a histogram, right? A bar chart, okay? Each category, to be a legal probability distribution, each category has to be mutually exclusive from each other. You cannot be in more than one bar chart. Okay. Second of all, those bars could not be negative. They always have to be positive. Okay. The next thing was every possibility that could possibly happen is in one of the bar charts. And then when we add up all the bar charts together, they add up to 1. And those were the rules of a legal discrete probability distribution. We talked a little bit about a uniform distribution where all the bars are equal height. Okay, but you can have probability distributions that look very, very different than that. We then went to continuous distributions. Okay, and in continuous distributions, the rules are we now have a line instead of bars. Okay, instead of having the bars add up to 1, the area under the line, the total area from minus infinity to positive infinity, the area under that line has to equal 1. Okay. In addition, that line can never go negative, just like the bar charts could never go negative. Okay. They can go to 0, but they can never go to negative numbers. Okay. All right. So that was primarily the rules for the continuous distribution to make that a legal distribution. Again, the area now has to equal 1. Obviously, when we do a continuous line, we are not looking at discrete things. We are always looking at rational numbers. So it's continuous. So between, let's say, 18 and 19, you can have every single possibility. 18.01, 18.07329797. We could pick out any random numbers, right? Everything is on that chart. Okay. Where in the discrete world, it didn't even have to be numbers. We could have bar charts like heads and tails, or we could have male or female, or we could have numbers, number of siblings, right? So there's a lot more things in the discrete world that aren't numbers. But when we do a continuous, the x-axis is always numerical, okay, with any combination thereof. In the continuous world, we looked at two distributions. The first distribution was the uniform distribution. It was 0, went up, and was flat, and then went back to 0. Okay. The good news behind that distribution is because everything is a rectangle. The first step usually is to figure out how high that bar is. And all we have to do is look at the big rectangle. The big rectangle from the lowest to the highest value, that width times the height has to equal 1. If we know what the width is, we know the difference between the highest and the lowest, the range, if you will, of those distributions. We know how high that line had to have been, because height times width has to equal 1 for the entire distribution. When we are looking for a probability of something specifically happening, okay, we look at the interval that we are interested in, and the probability of being in that interval is the area above that interval beneath the line, okay, which is again a rectangle. The width times the height is the probability. We just calculated the height a few seconds ago when we looked at the entire distribution. Now when we're looking at this shaded area, we know that height, we know the width, we can multiply them, and that'll give us the area, which is the probability of getting a result in that area, in between, in that interval. Notice, what's the width of a point? A point has no width. In a continuous distribution, the probability of getting any number exactly, I mean exactly, probability of getting 12 instead of 12.0000000001, which isn't 12 exactly. The probability of getting 12 exactly is the area above that point. 0 times any height equals what? 0 times anything equals 0, right? In a continuous probability distribution, the probability of getting any specific number exactly is 0. The probability of putting 12 gallons of gas in your tank exactly, not a drop more, not a drop less, not a half a drop more, never happens. Well, the probability is 0 that it happens. Okay, so we have that little bit. Okay, the uniform distribution was easy to work on because we can do it by hand, because you all remember height times width is the area. That came from high school, right? Okay. We then talked about the fact that there are a lot of other distributions, and the only other distribution that we are going to do in this class right now is the normal curve, or the normal curves would be a better way of stating it because they're family. You know, the uniform distribution was also a family of distributions because between any two numbers we can have, you know, a normal distribution with different starting spots and different ending spots, with then means different heights, right? So in both of these cases, they're families of distributions. Well, the normal distribution is almost impossible to calculate by hand. And so what we always do is use a table. Okay. The concepts are still the same. The probability is the area under the curve above the interval that we're interested in. Okay. So if we're interested in the probability of getting between 0.3 and 1.2, we look at that interval and shade up until we get to the normal curve, the line. It's not a rectangle. It's not an easy thing to calculate, right? So what do? We look at the tables. So we taught you how to use the z-table or the standard normal table, right? And we taught you a couple different tricks as to how to do that. First of all, how do you read it right off of the tables? And then second thing was, you know, given that you know, how do you deal with situations where what you are trying to find, the shaded area you're trying to find, isn't the area that the table is showing you, right? And we kind of talked about how to do those things. Okay. Then we went to the next step. The next step was that we admitted that real problems that we face in the real world are seldom the standard normal one that is in the back of the book, the one that is centered around 0 with a standard deviation of 1. They come from all sorts of distributions. Almost everything in nature is distributed as a normal distribution. Okay, and we'll explain a little bit about why that happens next time around. Well, in the next section, as we start the next section. Okay, but it turns out that we can do those, we can do almost any, so we can do any normal curve, even if it is not the standard normal, because we can find the decoder ring. The way that I strongly recommend is take a blank sheet of paper, put the problem that you're trying to solve up on top, including the distribution that you're pulling this from, where the mean is, what the mu is, and what the sigma is, okay, which should have been given to you by the person who gave you the problem to do, right? And then what you should do is right underneath that, draw the standard normal, centered around 0 with a sigma of 1. Okay, and you draw 1 up on here, 1 right underneath. Then any point that you had of interest on the top chart, draw dotted lines down, and we're going to find the corresponding spot on the standard normal. And that was the Z formula. Whatever the x is that you're trying to find the corresponding spot, x minus mu divided by sigma is that secret decoder ring that will find you the equivalent spot on the standard normal. Once you have the equivalent spots on the standard normal and you shaded the same areas as above, well, now with those z values, okay, that you just calculated with the decoder ring, you can look at those in the normal distribution table, just like we did in the first section. Okay. Now, the very last section of our probability part of this class dealt with scenarios where you weren't looking at the probability of getting just one item that you had pulled at random. But let's say you went fishing and you were going to go out and fish until you got 5 red snappers. And you are interested in what is the probability of the average of the 5 that you are randomly taking. You're not doing it randomly for one. You're taking 5 random samples, and then you're averaging them. It turns out you can use the normal tables with that, and what happens is that decoder ring, that decoder formula just has one more addition down in the bottom. Okay? The formula changed just a little bit. Okay? And by doing that, you can come up with the probability of getting all sorts of stuff. Right? Anyways, that pretty much ended stuff. Okay, well, just one more little bit. Theoretically, if I take one item from a distribution, isn't that a sample? And the answer is, yeah, theoretically it's a sample with a sample size of 1. Well, go look at the formula. The formula for the distribution of the sample means that decoder ring, if you substitute 1, you'll notice 1 goes away, and the formula is exactly the easier formula you saw before. Okay? Anyways, that's it. So we're going to have the test, and there'll be directions on the test. I am trying to figure out how to do this the simplest way, and if I can't find a better way of doing it, we will use the simple way, is I will put that test out on Blackboard. I will probably theoretically label it as an assignment, because that's how Blackboard likes to do these types of things. Take that test, print it out, answer it as if it were a written in-class test, and then take pictures of it or scan it in and upload it back onto Blackboard. Okay. I will have a 2-hour or an hour and a half time limit. Okay. So when you do it, I will be looking at when you downloaded the file and when you uploaded the file. And I probably will even put a little spot where you can write it on the tests, right? Okay, so that's the way that I'm planning on doing it. Okay, there's still a slight possibility I will do it with a multiple choice instead of problems. I'm kind of leaning against that right now because I think problems are the better way of solving these. All right. Anyways, with that, I wish you the best of luck on that. And, sometime on Wednesday, maybe Wednesday evening, the test should be available. And you should have until at least Friday night, midnight on Friday, to download it, do the test, upload it. It will be an open book test, okay? And you will need to have your Z tables and your table that was the binomial distribution table. Anyways, you're welcome to write whatever notes you want. There isn't a limit this time because honestly, I'm not going to be there to police it anyway, right? So it is technically an open book. It is not an open communications. You may not talk to anyone, right? So you can't make it a group project. As a matter of fact, some of you may have a different test than the other one. Okay, just like we did on the physical tests where not everybody opens up and gets the exact same test. And so if you provide a perfect test for a test that wasn't given to you but was given to somebody else, okay, that's a good way of getting kicked out of school. Okay. Anyways, I don't think that that's going to happen, but that's where we're at. Wish you the best of luck, and after this, we will open up a new section of the class. In the new section of the class, we're not doing probability anymore. Okay. In probability, we knew the rules of the road, right? We knew that the probability of getting ahead was 50-50. We just didn't know whether we were going to get a heads or tails. Or if we did it 8 times, we didn't know, whether we were going to get 6 heads or 3 heads or no heads at all, right? But we knew the rules of the nature, right? Probability. We know the rules. We just don't know what's going to happen, right? The next section is going to be called inferential statistics. In inferential statistics, we won't know the rules. We're going to have to guess what the rules are based on what we have seen from our behaviors and from our samples. So we are then trying to figure out what God's rules really are. All right. So that's going to be the next section. After this test, that's where we're going. All right. With that, I hope you're having a good time, and good luck to you on your test. Thanks. Bye-bye.